All right, let's dive right in. Today, we are going to crack a math problem that, honestly, looks like a total nightmare. But I promise you, by the end of this, you'll see it's way simpler than it looks. So, let's treat this like we're detectives on a case. In our first piece of evidence, it's this angle that seems like it was specifically designed to be confusing. And there it is, our main suspect, sine of 31 pi over 3. Now, I get it, your first instinct might be to just kind of panic a little. 31 pi over 3, who has that memorized? Well, here's the good news, you don't have to. Yeah, this is definitely not your everyday pi over 6 or pi over 4. The secret to cracking this case isn't about brute force memorization. It's about finding a hidden pattern and simplifying the whole thing before you even get started. Every good detective has a secret weapon, right? Well, for this mystery, ours is a core property of the sine function itself. This is the one clue that's going to blow this entire case wide open. So what on earth is periodicity? Well, just picture a sine wave in your head. It goes up, it goes down, and then it starts over, doing the exact same thing again and again and again. That one complete cycle, that repeating pattern, has a length of 2 pi. And that leads us to this incredibly useful rule. Now, this might look a bit formal, but all it's saying is this. If you take any angle, that's our theta, and you add any number of full circles to it, that's the 2n pi part, you land right back in the exact same spot. So the sine value doesn't change one bit. It means we can simplify a crazy number of angles down to just one simple cycle. Okay, it's time to put our secret weapon to work. We're going to take that intimidating fraction and see what it's really hiding. We've got a clear three-step plan. First, we'll rewrite that angle into a form that's actually useful. Second, we'll apply our periodicity rule. And finally, we'll boil it all down to a friendly angle that we all recognize. All right, step 1. Here's our original angle one more time, 31 pi over 3. Our mission is to break this improper fraction apart. And here's the trick. We just look for the biggest number inside 31 that's easily divisible by our denominator, 3. And of course, that's 30. So we can just split 31 pi into two pieces, 30 pi and pi. And when you divide both of those parts by 3, look what happens. We get this much friendlier expression, 10 pi plus pi over 3. This is exactly what we were looking for. We've got a nice, clean multiple of pi, and then a simple, familiar fraction left over. Now for step 2. That 10 pi is the key here. What is 10 pi, really? It's just 5 full laps around the unit circle, 5 complete rotations that end up right back where they started. So because of periodicity, its effect on the final sine value is nothing. We can literally just get rid of it. This means our original, super complicated problem has totally changed. All those extra spins around the circle don't matter at all. So what are we actually left with? That's it. All of that complexity, all those numbers, they just melt away because of periodicity. And we're left with this simple, familiar expression. This is the aha moment, where the case just breaks wide open. We've done the hard work. The investigation is officially over. Now all that's left to do is reveal the simple, elegant solution. Just take a second to appreciate this transformation. We started with sine of 31 pi over 3. And by using just one core concept, we've proved it's the exact same thing as sine of pi over 3. And this is a question we can answer. This is one of those standard angles you see on the unit circle all the time. Pi over 3 radians is just 60 degrees. And the sine of pi over 3 is the square root of 3 over 2. Case closed. That is our answer. That whole intimidating beast of a problem boils all the way down to this. So what's the big lesson here? The next time you see a trig problem that looks scary, don't panic. Just remember this method. Look for the simple pattern hiding underneath, in this case periodicity, break the fraction down, pull out all the full circles, and simplify it to something you know. And that leaves us with one last question to chew on. Sine isn't the only function with this kind of secret power. Cosine has it too. So do tangent and cotangent, even though their periods are a bit different. It really makes you wonder, what other patterns are out there, hiding in plain sight, just waiting to make the next complex problem a whole lot easier?